Good one, Kevin.
Oh,
dude, that means I can't talk, right?
no. That means talk more.
I'm on camera.
Okay. All right. All right. First, let's walk through the basic problems I want to go through today.
We're rakes back here.
So
it is just terrible.
All right. So here's the idea. We're going to be talking about basically number one, increasing and decreasing functions. I introduced that last Friday. I want to continue with that today, and then get to a brand new topic that we really haven't discussed yet that you need to know. It's kind of difficult, but I'm going to try my best to explain the concept of what we're doing here today. So that way, when you get there, you might think it's easy. But it's one of those things you just need to see it. So let's see, where's my cursor at?
Literally terrible.
Where is it? So
don't bring that in home.
Hey, there it is. Okay.
I can taste it. I can taste the salty beyond the air here. Shh.
Okay. So here's the idea. First step here. I want to talk about increasing and decreasing functions. So here's my first example I want to talk about. Okay. So here's my first graph. This is a discontinuous graph. It has breaks in the graph, and the trick is, I know that the last couple days here where we talk about, domain and range, max and mins and all that good stuff. But this particular graph talks about where is this graph going to be decreasing, where is it increasing, and where is it constant in no particular order. And that's the new stuff we introduced Friday. Now, to do this, we have to use interval notation. Interval notation is that idea of like using parentheses and brackets, but it's only using x numbers. So it's using the x's, not the y answers. So you got to get through your head. This is the hardest part. Is you got to look at it. You got to look at the graph. You're not using any y numbers at all. You're just using the x's going horizontal. Okay? And so there's three parts that I want to talk about here. Let's talk about increasing first. Is there any part of this graph, as I go from left to right, where it's going up?
Yes.
Where?
1, 2, 3, 4.
Okay, so it starts at 4, and where does it go?
To the right.
Infinity. Towards infinity. Now, it's not just because the arrow's going up, it's because the arrow's going horizontal, it's going towards the x numbers, which are infinity. So, how do you write this? It's going to have a parenthesis with the number 4. Why it's a parenthesis is because that's an open circle, so we use a parenthesis, and it's going up towards positive infinity. Okay, does that make sense?
Uh-huh.
Now, infinity has a parenthesis, it's not a number, it's a direction. Again, I'm using the x's to state where this thing is increasing. It is increasing here, it's going up. So I'm using the x number, starting at 4, going up. Now, this thing was decreasing for a little bit.
Huh.
There was a small section here where it was decreasing.
-2 to 1.
Okay, good. So -2 up to 1, and we're using brackets. So, -2 to +1, and we use brackets. Those are closed circles, we can use brackets. The back of the book typically doesn't do the bracket or parenthesis idea. They just use parentheses on everything. It's still using correct interval notation, so use the brackets. Because they are closed circles, so we can include them. And then this thing also has something new which we did not discuss last Friday. It is constant at one point where it's flat. So it is constant where there's neither growth nor decay. So in this case, we're at -infinity up to, what is this, -5, and that's a parenthesis. Now, this is the one that most people get wrong, not because it's constant, because you got to remember, you have to go left to right. The leftmost number is -infinity up to -5, and it's a parenthesis there.
You put the check mark because people get it wrong?
People get it wrong, a lot. So, they get that one wrong because they switch the two numbers around. They go -5 to -infinity.
That's wrong.
You have to go left to right.
Okay.
See you later.
See ya.
Bye, Crip.
Bye.
Hey, video will be online tonight.
Okay.
I checked, all the videos are online and make sure they're all working. I checked last night, they are all there. So look, hit refresh. They're not, they are all there. Okay, all right. Questions on the intervals. Okay, now here's the thing. One of the things we discussed on Friday was what happens, not when there's overlap, but when they share numbers. And that was one of the goofiest part, is when you share numbers, you don't use brackets anymore. Even though there might be solid dots, if a number is being shared between increasing and decreasing, you could just have a parenthesis in a certain location. Okay, but is there any questions with this constant decreasing and increasing?
No.
Okay, all right. Let's go to another one here. Okay, this is still the first problem, but let's do a thing where it's kind of sharing here. Okay, let's do that. Okay, so different graphs. It is for the most part, this graph is continuous over a certain viewing window. It is, not completely continuous because the left side there's still a break. But over a viewing window, this thing could consider to be continuous because it is actually traveling. Now, let's talk about whether this thing is increasing anywhere, and where it would be found increasing, going up from left to right. So left to right, as I go
to infinity.
Yes, right here, up towards infinity on the x's, right? Now, here's the weird part. I know it's a closed circle, right? But the problem is that dot is literally shared from the increasing to the constant, right? This number is being shared with constants and increasing, so you can't consider it to be in one or the other. So it has to be a parenthesis at 1.
Huh.
And then it goes up to positive infinity. And the weird part about doing that is because it is being shared. If this was disconnected right here, you could put a bracket. But since it's shared between constant and the other, you'd have to put a parenthesis there. Now, decreasing. Okay, it's decreasing from -4 up to -1.
That's that.
And
right.
-1 is a parenthesis because it is being shared. The -1 is being shared with the constant next to it. I know that's really tough. And again, I'm using X numbers, not Y numbers. So get out of your head, I'm using Y answers. And now the constant on this graph is, again, this is the new part we have never discussed yet. The constant on this graph is from -1 to 1. And again, I'm using parentheses because those two end caps are shared with decreasing and increasing.
Oh.
Now, I don't even care at some point if this thing did one of these, where it came up to a point, went from here to here, and then suddenly it took off at a different angle. It is still increasing. I don't need to break up anytime it switches like slope. So that would still be from 1 to infinity increasing.
What if it went straight up?
Straight up, still increasing. It's going up.
So it's still to infinity.
It's still increasing because there's probably a slight tilt to it. If it looks like it's perfectly vertical, it's just that one number from 1 to 1.
Bracket.
Because I've never seen one where they just put it straight vertical. It's increasing. It's just I've never seen it where it's straight vertical. Usually they put it tilt on. Question.
Dude, you gotta speak
something
up.
like this.
Yeah.
You still use parentheses because it's still being shared. Yeah. So this point, it was increasing from 1 to positive infinity, the decreasing from 4 up to 1, and it would still be a parenthesis. And there would be no constants on the graph. All right. Questions? That's a good question.
You scared me.
Like up and down, up and down, up and down. Okay. So great question. So if this thing is, so if you didn't hear Kevin, he was asking like, what if it's doing stuff like this, where it's going up and down, up and down, up and down? You'd have to list all those different like gaps where it's actually increasing. So like, I know it's increasing over multiple times here.
So it'd be
it's increasing up to this point, it's increasing here, it's increasing from here and on. So you just do a bunch of unions with all those different sets. They probably, since it's going up and down constantly, you're probably using a lot of parentheses, just because it's being shared with increasing and decreasing. But yeah, so you go from like, if it was increasing from -infinity up to this, -11, and then it was decreasing for a little while, and then maybe this is -7, so I'd go a union. So I'm still doing the increasing. So union, -7 up to, what is that, -4. And notice I'm using a bunch of parentheses because they're being shared, because the next stop would be going down. And then it went from union again, 1 to infinity. that mean where it's kind of go up and down. Just give me the select parts. Yeah, these are good questions. Anything else? That was good though. Okay, now obviously this is like a rerun, like kind of like reviewing what we did last week. Throwing the constant in there now, throwing in when you use parentheses and brackets. Basically brackets are anytime you have an end cap. You have an end point. Okay. Now, let's go with the last type of problem here. We're going to do two of these, potentially. I want to talk about what they call a differential quotient. Okay, this is brand new. You need to write this down. In fact, you need to write down the formula. This is one of the parts that this is your first step into pre-calc, like actual calc material. So, differential quotient.
Are we dividing now?
Okay, kind of, not really. We're going to see kind of a weird thing here. This has a purpose. I'm going to try to explain the best I can. The first class eventually understood it. It's tough to look at first. It's tough to like wrap your head around like, what are we doing? How do we calculate? What is this thing even for? I'm going to try to connect all the dots as we go. I'm going to try to do an easy one and then kind of the more like traditional problem you see. This is the formula for a differential quotient. I'll just let you write this down. This is something that if it was on a test, which it will be, this would be printed in the instructions up above. Says, use the following differential quotient to find the value for the following function. Okay, so this is the formula. It's f of x plus h minus f of x all divided by h. I'll let you write that down. Then we're going to talk about what this is. Because it looks big and it looks weird. I'm going to explain why it relates to the stuff we just did.
You done filming?
No. No, it's one of those things like the camera, the camera's set up in such a way that it only records like 23 minutes.
Why?
So it's just the way that the camera works so it can actually store on the memory cards. And so like I have to like turn it off and on.
Wait,
like
you knew that was 23 minutes?
No. It's just I always just stop it after like 10 or 15 when I'm like changing up problems. So that way I can make sure that the whole video's there. I just attach them together because if I just let it go, it will turn off. Like after 23 minutes, it just stops. And I look up and I'm like, oh, the camera's not working because it probably was 23 minutes. So
well, that's pointless.
Yeah, it was just one of those things. It was just that's the fault of the camera.
Why'd you get it for 41 minutes then?
I can get cameras that go longer. It's just, I wanted the highest quality as possible. So.
I can make you one.
Okay, hey, let's talk about differential quotient. So here's what we're gonna do. This is gonna be my function to begin with. So what I like to write down is this function right here. Now this is going to be very easy. I'm going to explain the concept here in a second. Okay, so this is my function. Now instead of a y, they can write it as an f of x. Oh, that means the same thing. Now, let me explain what we're looking at here. Okay, and then I'll explain what's going to happen. Okay, when you do this problem, and this is my function, I can go and graph this. What type of graph would this look like?
Slope.
Okay, you're starting to see it, right? It's got slope. It's literally slope intercept form. It's a line that you did back in Algebra 1, Algebra 2 days.
Right, yeah.
Okay, yeah, that's fine. So I'll just explain the rough concept here. We're not drawing lines or anything. This is just to help you explain, like, what are we doing with this? What this is, again, if I draw this picture, this is a line. It's starting at the y-intercept of 1. My slope is 3. That's what y equals mx plus b, right? So this 1 is the y-intercept number. And my slope is the number 3, but you can make any number fraction, so it's 3 over 1. So that means I rise 3 over 1. Okay, so rise 3 over 1, rise 3 over 1. All right, so here's the graph of what this thing looks like. Now, do you agree that it's linear?
Yeah.
Okay, here's the thing. Here's my question when you look at that picture. Does my graph have a maximum?
No.
No. Here's why. Because it's linear. It's literally climbing the entire time from left to right. So this doesn't have a maximum. What the differential quotient will help you find is if there's a maximum or a minimum to a graph. It will tell you, even if you have like this crazy curve going on, like where it's going up and down constantly, this formula will literally tell you where the peaks and valleys are on any type of formula that we have. Okay? That's what it's going to do. Okay? Now, the hard part is, you have to see what it's going to spit out. It's not going to just spit out the maximum, because I'm going to show you what it's going to spit out for this problem. And then you got to wrap your head around why it's spitting out this certain number. So I'm going to leave that on the board. This is just an example. I'm going to use this function to help you identify what this formula actually spits out and why that's actually helpful. Okay? So here's my formula. So what we're going to do here is I'm going to do the differential quotient for 3x plus 1. So that's my formula. Does everyone understand this is what I'm using?
Yes.
Okay, so what we're going to do is we're going to write down the original function, but we're going to plug in x plus h into any spots where there's x's. So,
You read 3x plus 1?
so the 3x plus 1, right? So I'm going to take out the original x on the 3x plus 1, and I'm going to substitute in an x plus h into that spot. Does that make sense what I'm doing? It's the original function with x plus h substituted in. Okay? The next thing I'm going to do is I'm going to subtract the original function of. That's what subtracting f of x means. So what was my original function?
3x
Plus 1, right?
plus 1.
Okay, that's my original function. And then it's all divided by h. Now, to explain what h is this idea of like, you're trying to get closer and closer to where the hills and valleys are. So what they're going to try to do is make h as small as possible. So it's like this fictitious number, like if I can be within, you know, like this is a hilltop, if I can be within a certain h boundary of the hilltop, I can find where the hilltop is. And I want to make the h as small as possible so I can pinpoint where that hilltop is. Okay? So here's the formula. So here's what you're looking at, right? I'm gonna just do some simple math, some simple algebra, and simplify this thing down and show you what this differential quotient spits out and why that's important. Okay, so I'm going to distribute the 3, just doing some simple math, distribute the negative sign back here, just doing normal stuff here. So that turns out to be 3x plus 3h, right? Plus 1 minus 3x minus 1 all over h. Okay, hopefully you can see that. Let me lower this.
Oh, it's
Okay.
right, loud.
All right, so I've distributed the 3, distributed the negative sign to the back. Here's what I have. Here's how you know if you're doing the differential quotient correct so far. At this point, what will happen is anything that does not have an h should cancel out. And that's how you know if you're doing this right. Well, let's look at this. 3x's literally cancel out. The 1's literally cancel, and all I'm left with are things with h's.
So it's 2h.
And I have an h on the bottom, right? Because I'm divided by h's. So when I divide, what you get is you just get the h's canceled, and I'm left with 3. Now you're thinking, Ward, what is that number? What you're looking at there, and I know this seems silly for this problem, it's going to spit out slope. Now you're thinking, Ward, I didn't use slope. You told me what slope was in the beginning. For an easy problem, you can identify slope. But if this thing was a curve going up and down, slope changes. Slope will go positive, it'll go negative, it'll go positive. And why this is useful, if I can identify where slope turns out to be 0, because on a hilltop, slope is 0. It went from positive numbers to negative numbers. At some point, it hit 0. So if I can identify all the spots where slope is 0, that's where the hills and valleys are. Well, on your graph, can I make the number 3 a 0?
No.
No, there's not even an x to plug in, right? So I can't even make this a 0, so that means there's no hills and valleys to this problem. You're looking at the picture. Does that have a hill or valley?
No.
No. Okay, so you're thinking, Ward, why did we do all that work?
It's got a big hill.
Okay, so here's the idea.
It's a mountain.
Let's do another example here, where now, I'm going to leave this on the board. We'll do it for another one that does have a hill or valley, so you can see how to use it now.
Perfect.
So, here we go. So let's go to the next example. Let's go with 3x squared plus 4x plus 1. Okay, so I'm going to write down that problem. Okay?
Bless you.
Okay, we're going to do the differential quotient here. Now, what I'm going to show you with this drawing, because I'm going to draw it in a little bit, the drawing is the stuff you've learned in the next chapter, chapter 2. We learn all these strategies to draw random formulas. Like there's a lot of rules we follow. I'm just going to factor this apart, figure out x-intercepts. That's something you probably already know how to do. Factoring this apart, that's 3x and 1x plus 1 and 1, and that makes the 4 in the middle. That's a trinomial, I factor it. So what each of these would be, this would be a -1, this would be a -1/3. So there's a -1, this is a -1/3. And my y-intercept is 1. You learn all this in the next chapter. And so this is what we're looking at. This is what my curve looks like. Okay? And I know it's that way. It's a parabola. It's got a power of 2. That's something you learned in algebra 2. But there is a hill and valley to this thing. It is literally turning around at some point. Now, what we're going to figure out is where exactly did it do its turn? Where was that exact number where the hill and valley is? Because how to tie this back into your homework, and like what we've been talking about, we were talking about where this thing is increasing, decreasing, right? This was decreasing, and then suddenly it changed to increasing. We are literally trying to find the exact moment when it switched from decreasing to increasing, or vice versa. That's why they have you learn this in this section. Now, there's a ton of other stuff we can use this stuff for. Like, it is massively important. In fact, they use this differential quotient literally every day in Calc 1. Like, it's used for tons of different things and purposes. But the main thing you need to remember is it will spit out slope, a formula to find slope, and what I need to do is figure out where slope would be 0. Where would it be its valley or hilltop? Questions?
So how did you get the negative 1/3 and negative 1?
Factoring it apart. So just doing old school factoring, it's a trinomial, 2 parentheses, plus plus. Breaking up 3x to be 3x and 1x.
Yeah.
Breaking up the 1 to be 1 and 1. And it does make 4. And then what you do to solve for x-intercepts, you just set these equal to 0. And you just solve each one for 0.
Oh.
So that stuff, we're going to get that in the next chapter. Don't worry about it. Okay, I'm doing it all at once so I can draw it really quick.
Yeah, I remember it now, Mr. Will.
Oh, okay, well there you go. We will review, so if you're like, I don't know that, it's coming, chapter 2, calm down. Okay, now.
Take a cheer to it, bro.
Yeah, we'll get it. Now, let's apply this formula so you can see how this works, and this is my last prompt of the day. This is it. So we're going to do all this stuff. Okay, we're going to do the differential quotient for that problem now. Okay, so again, we're looking at this function, and that's what we're trying to find. We're trying to find where that minimum spot was on my graph. Okay, so first thing, I need to plug in x plus h into all the x's you see on that formula. So my formula is 3x plus h squared plus 4 times x plus h and then plus 1. That's the original function with all x plus h's plugged in, where there's an x. Then what I have to do next is I always have to subtract the original function. What was my original function over there?
3x squared
Plus
4x
plus 1.
plus 1.
Okay, and that's all over h. Okay, does everyone understand how I set that up?
Yeah.
We'll do some more of these tomorrow as well. That way we get the setup. The setup is the hard part. Like, can you write it down with all the x's taken out, with x plus h's plugged in? Can you subtract the original thing off? All right, so now, this is where all the math comes in. Can we do the simple math that we've learned over years of doing Algebra 1 and 2? This part right here is the hard part. You have to FOIL these two together.
X squared.
So it's x plus h, and then we have to distribute a power of 3 over it. I'm going to do this all for you in one swoop.
2.
So x times x is x squared, x times h is xh, h times x is hx, and h times h is h squared. And then what I'm going to have to do is, now that I've FOILed that together, I have to distribute a 3 over all of that. 3, 3, 3, and 3. Does that make sense? Foiling it, distributing 3 over it at once. These can add together, so that can make 6's, but you get the idea. Right here, distribute the 4 over that parenthesis. 4x plus 4h. Add the plus 1. Now, back here, I'm going to distribute the negative sign. Negative 3x squared minus 4x minus 1. And this is all over h. Here's how you know if you did it right. If you're doing all this stuff, you're distributing, you're doing everything. Anything that does not have an h will go away. That's how you know if you're doing it right. Anything that doesn't have an h should cancel out. So if you did this right, so 3x squared, negative 3x squared, 1, negative 1, 4x, and negative 4x. They are literally all canceling. So what I'm left with is 3xh plus 3hx, which I can add those two together if I wanted to, plus 3h squared plus 4h. And that's all over h. Okay, makes sense so far? For the most part, anyway. Because, again, this is the first day of you ever seen this. The next step I'll do is I'm going to divide everything by h's. Literally everything, one at a time by h. Since everything is an h, I can divide every h off. And what I'm left with here is something simplified. It's not final, but it's simplified. So 3x divided by h is 3x. 3hx divided by h is 3x. 3h squared divided by h is 3h. And 4h divided by h is 4. Okay, so far so good? Okay. Now, what did I say earlier? What do we want to make these h's so that I can get closer and closer to the hilltop? Okay, I want to make them as small as possible. When I can make h a 0, that's where I'll be right on the hilltop. Well, if I make h 0, that would literally go away. It would literally cancel. If h was 0 or really small numbers, like tiny, tiny small numbers, that number would literally turn out to be a 0 if I made that small enough. So that means I'm left with this. 6x plus 4. If h literally turned out to be a 0, where the hilltop is. Now, why this is important. This will tell me, this thing right here is the slope. It will tell me where my hills and valleys are. It's not a number. It actually has an x on it. That means I can actually figure out where my slope would be 0.
2/3.
So set this equal to 0 and figure out where the hilltop is. Where would slope be 0? Because again, this is slope once h turns out to be 0. So you divide this over, or sorry, subtract that over, that's negative 4. Divide by 6, and I get negative 2/3. That is this number right there. Negative 2/3 is my x number. That is literally x where that thing changed from decreasing to increasing. That's the exact moment where it happened. Now, again, that's assuming that my slope was 0 at that exact moment. Now, if I want to find the y number, the exact height, all you have to do is take the negative 0.6 for being negative 2/3 and plug it in here. And that will give you what your other numbers are.
Let me tell you.
Question?
So what did you, like you talked about the 3h?
Yeah, because what we want to do is get to the hilltops, right? That's where the h, that's like that weird distance. We want to make h as small as possible. We make it 0, so we land right on the hilltop. So if there's any h's left in that problem, you literally cancel them out and make them zeros.
Seems simple enough.
Negative third.
Negative third.
Is that right?
Is that your y again?
Yeah.
That's the one.
2 homogeneous.
I did.
Well, that was a good question. That was a really good question. Or, hey, now, again, here's the thing. Don't be frustrated. Like, this is the first day you've ever seen this. This is something that I've done years of. Like, it was something that you do for an entire semester of Calc 1. This is your first taste at real calculus. Like, the first baby steps into it. Now, again, this is the intro day. Don't feel like you're overwhelmed. We're going to do a lot of these tomorrow to make sure that you get familiar in what to do, why we cancel all h's, why we do little things. So, that's what we're going to do.
Do you cut this part out where you walk to it?
Nope.